Twinspan, or two-way indicator species analysis, is a classification method developed by British ecologist Mark O. Hill in the late 1970s. In my experience, it was an exceptionally well-crafted piece of work for its time, in some sense, even bordering on a work of art. In certain cases, it still ranks among the most effective classification methods for vegetation data. Although Mark Hill made his original Fortran program freely available, it took quite some time before it was translated into more modern programming environments. Eventually, Jari Oksanen succeeded in doing so, creating an R implementation that he published on GitHub. However, since the package is not available on the official CRAN repository and is not regularly maintained for newer versions of R, users must compile it themselves before first use.
To compile the package, you first need to install R Tools, which is available on the official website of the R project. Once R Tools is installed, the package can be compiled and installed directly from GitHub within the R environment. Only after that can you launch the Juice.net program. If you're using R within Juice.net for the first time, go to the Options menu, then to the External Program Paths tab, and select the version of R that also has R Tools installed. Then, in the Analysis menu, choose the option Twinspan Classification.
At this stage, you set the individual parameters of the analysis. The most important of these is the number of pseudospecies. This concept offers an elegant way to make an algorithm based on presence-absence data partially account for species cover as well. If you assign multiple pseudospecies to a single species, each one is treated as a separate row in the data matrix. This row will contain zeros where the species cover does not reach the given threshold, and ones where the threshold is exceeded. For example, a pseudospecies with a cover threshold of 25 would be represented in the table like this.
Another important parameter is the number of clusters. In the original version of the Twinspan algorithm, a binary split occurs at each step. Every group of samples is divided into two subgroups. The result is a hierarchical structure, where the number of groups increases as powers of 2, 4, 8, 16, 32, and so on. However, in this mode, the user has no direct control over the final number of resulting groups, as it depends on the depth of the splits and other internal parameters of the algorithm. In more recent implementations, this logic has been adjusted to allow users to set a target number of clusters directly. Among other things, this makes it easier to compare the output of Twinspan with the results of other classification methods that work with a predefined number of groups, such as k-means or hierarchical clustering.
When you run the Twinspan function for the first time, the analysis may take a bit longer, since the necessary library must be compiled first. I recommend starting with a sample dataset, just to make sure everything is working correctly. Once the calculation is complete, a list of available cluster numbers will appear. Simply click on the desired row, and the table will show separators that define the boundaries between groups. Your file is now ready for further analysis.